Okay, we're going to get started with the next talk. Please welcome Matthew Garrett from CoreOS.
Hi, thanks for coming along. So, as Ed mentioned, my name's Matthew Garrett. I'm a security developer at CoreOS. And today I'm going to be talking about the distributed trusted computing technology that we've been developing. Now, one of the core, if you will, aspects of CoreOS is that we are very focused on security. We care so much about security that the About page on our website leads with security. Just in case that's not obvious enough, we're pretty definitively stating that we are about security. And there are several reasons that we think that CoreOS is important and relevant in terms of security. And amongst those, well, obviously, CoreOS is to a large extent about containers. And there's been a lot of discussions in the past, including some from me, comparing containers to virtual machines and the amount of isolation that they offer. And that's not really the relevant comparison. When we are talking about the security of containers, we're typically not comparing situations where people are otherwise deploying entire VMs. We're talking about situations where people are running their web server and their database on the same system. We're talking about scenarios where you have multiple independent components that are running within the same namespace. They're running isolated by nothing more than the fact that they're running as separate users, if you're lucky. If you're unlucky, all these services are running as the same user, and in that case, compromise of one is compromise of everything. So compared to this kind of deployment, containers give you greater isolation. And the combination of namespaces themselves, the kernel's base level functionality that enables containers, if someone is able to execute code as, say, your web server, the kernel should still isolate them within that namespace. They should be unable to interfere with any processes that are running in other namespaces, i.e. processes that are running in different containers or processes that are running in the host system. So from that perspective, we already have additional security. But we can go further in that every container can be run as an independent SE Linux context. And that gets you most of the power of SE Linux without any of the drawbacks. Your web server is now running in a completely different SE Linux domain. It's got access to everything that you want it to have access to by virtue of that being incorporated into the container. But it's not able to interfere with other processes, and effectively within the container, there's no SE Linux restriction. The only SE Linux restriction is on interactions between containers or interactions between the container and the host. So you've got this security that SE Linux gives you without the administrative or maintenance overhead that SE Linux typically gives you. So we're already at the point where containers can help you with your security. But there's more than that. If you're deploying containers on CoreOS, suddenly your application update story and your operating system upgrade story look very similar. So you've got a cluster of systems, and they're running a cluster of containers. We're no longer talking about an individual system being particularly special. And that means that the operating system that an individual system is running should not be particularly special. Right now, if you're in a situation where you want to upgrade to a new version of an operating system, you'd typically have to spend some time testing that new version of the operating system. And you're always going to be concerned about whether that test environment directly duplicates your production environment. When everything is containerized, the underlying operating system is much less important. So with CoreOS, you can upgrade a small percentage of your systems in production. And if something goes wrong, you just roll those back to the old version. If everything's good, you just push that upgrade out over more of your machines, and eventually everything's running the new version. And that way, as Greg mentioned in his keynote yesterday, one of the most important things is making sure that your kernel is up to date, and that running old versions of kernels is, from a security perspective, an absolute disaster. Taking this approach means that you can gradually push out the kernel until you feel absolutely confident that there are no issues with it. You can push out the entire new version of the operating system without that concern. And this makes it much easier, much more relaxing, much less stressful to get your new containers out there. Your new operating system out there. And another aspect of the general overall improvement of security that you get from containers is the ease of having a cryptographically verifiable deployment. CoreOS is signed. All the updates are signed. You can, if you want, use your own root of trust rather than using our root of trust. And so, wonderful. You don't have to worry about verifying individual operating system components. You only have to worry about verifying the entire operating system. Rocket supports cryptographically verifying your container images, and it does that using very standard tooling. If you want to sign your images, if you want to configure your node so they only run images signed by you, that's fine. It's just GPG. This is trivial. So if you are in a scenario where you want to make sure that your nodes will only run containers that you have authorized, great. It's much easier to do this than it is to do the same thing at the traditional kind of package-based deployment level. But there's a problem here. And the problem is that when we're talking about this kind of cryptographic validation, there's a single component that's performing that cryptographic validation. If your container runtime is itself not secure, if someone has in some way been able to tamper with your container runtime, you can't guarantee that it is verifying containers. You can't guarantee that it is running unmodified containers. It is possible that your container runtime would deliberately inject backdoors into your container. So the absence of any way of verifying your container runtime means that you can't have any faith in the security of the containers themselves. So how can we verify the container runtime? And in CoreOS, we've added support for using something called dmverity, which gives you cryptographic validation of file systems. So if anybody modifies the underlying file system, the kernel notices this, and it's basically equivalent to you getting a read error from your disk. It fails, Rocket will never launch. Wonderful. So we can say, because of this, we have the technology to ensure that the container runtime is unmodified, has not been tampered with, and therefore you can trust it to run your containers. Except that's dependent upon the operating system performing that validation correctly. If someone's able to tamper with your operating system, they could disable this functionality. So we need some mechanism to verify that the operating system itself is secure. And functionality like UEFI Secure Boot provides a mechanism for doing this. You have a signed boot chain, and if anybody attempts to tamper with the operating system, the firmware will refuse to boot the operating system. So excellent, we have the technology to ensure that your operating system has not been tampered with, and because you can trust the operating system, you can trust the container runtime. That sounds like a problem that's basically solved, except the firmware is the thing performing the validation of the operating system. If you have no mechanism to verify that the firmware has not been tampered with, you have no means of verifying that the operating system has not been tampered with, which means you have no mechanism that allows you to verify that the container runtime has not been tampered with, and therefore your containers are not inherently trustworthy. Today, I'm going to be talking about technology that allows you to verify all of these things and more, starting with the firmware. Now, those of you with strong critical analysis will realize that regardless of how much we can verify the firmware, if the CPU is not something that we can trust, then it doesn't matter if the firmware is something that we believe we can trust. I'm going to declare being worried about deliberately backdoored CPUs to be out of scope for this conversation. If you're in a situation where Intel are making your life unhappy, you've really annoyed the wrong people. So, The aim here is to perform verification of as many components as possible from the moment you hit the power switch on the system. We want to be able to verify that the firmware is secure. We want to be able to verify that the operating system has not been tampered with. We want to be able to verify that your containers have not been tampered with. And doing this from initial power on is not something that we can just solve in the operating system. This is something that needs assistance from the hardware. And trusted computing is a term that describes the technologies that we're going to be talking about today, the technologies that allow us to have this verification from the point where we hit the power switch. In the mid-2000s, trusted computing started appearing. There was a lot of conversation about this. Microsoft were talking about this very publicly in something that they called the Palladium project. And the concern at the time, especially amongst the free software community, was that trusted computing was effectively a mechanism to restrict the way people use computers. It was going to be something that would prevent you accessing websites unless you were running the correct operating system. And in theory, yes, the technologies I'm going to be discussing could be used that way. In practice, they haven't been for a large number of reasons. It's pretty much impossible to use trusted computing in the wild, outside controlled scenarios. And that means that its power as something to restrict users is very limited. But today, we are genuinely concerned about security. We have reason to believe that services we use may have been tampered with by organizations that do not have our best interests at heart. And so the security side of this becomes much more interesting. And trusted computing is, as a result, something that we're looking at much more closely now, something that is being looked at as a way of protecting people rather than restricting them. The heart of trusted computing is a device called a trusted platform module. Trusted platform module is a small chip, it's about this big, really quite small, that sits on your system motherboard. The trusted platform module is a very restricted device in terms of its scope. The trusted platform module is not able to do anything itself. It cannot reach out to the operating system and stop the operating system from doing anything. It cannot examine the contents of your memory. It cannot alter the contents of your memory. The trusted platform module only knows things that it has been told. So that sounds like a slightly strange position to start with. If the device only knows what it's been told, how can we use it to verify that the system has not been tampered with? What if something just lies to the trusted platform module? The way we get around this is a process called measurement. And measurement, or measured boot, is a process where for every stage of the boot, we take a hash, and in TPM 1.2 devices, this is SHA-1. On TPM 2 devices, this is SHA-256 or better. We take that hash, that cryptographic hash, and that means that if anybody has modified the next component, that hash will change. So to begin with, we're already at the point where we're trying to store information about what we booted in the TPM. If we were just able to write arbitrary values into the TPM, this wouldn't be particularly useful. If someone managed to get some untrusted code running, they could just go back and overwrite the values that are in the TPM with the values that you expected to be in the TPM. And that would sort of defeat the point. So the TPM doesn't allow you to write these hash values directly into it. Instead, the current value in the TPM has the new value appended. So for SHA-1, you have a 20-byte value in the TPM. You have a 20-byte hash. You put those together, and you now have a 40-byte value. You take the hash of that, and you store that hash in the TPM. And this means that you only get a specific value in the TPM if you perform the same series of writes. Or alternatively, if you've managed to break SHA-1. Has anyone here broken SHA-1? Good. Yeah. Anyway, so I think that gives us confidence that SHA-1 is entirely sufficient for this purpose. So we now have a situation where the TPM contains a set of values. Every part of the boot process has measured the next component and pushed that value into the TPM. And the hash values in the TPM therefore provide a record of what was booted. But more than that, rather than just having the values that are directly in the TPM, we also have a log. And the log is just an area of RAM where we store the value that was written into the TPM and a description of what was measured. Traditionally, this has been kind of handled in we measure each component into an individual register on the TPM. But in CoreOS, we've taken a slightly more aggressive approach. We measure a lot. When grub, our bootloader, is loaded, we don't just measure the kernel that's loaded. We don't just measure the RAM disk that's loaded. We measure every command that is executed within grub. We measure every bit of the configuration. We measure the configuration that is passed to the kernel, which means we have a full record of everything that happened in the early boot process. Anything that anybody could have potentially tampered with is measured. That means that we know exactly what state the system was in when control was handed off to the operating system. Our problem with this log file, as I said, is that the log file is just in RAM. And if someone manages to get untrusted code running, they're able to overwrite the log file. But there's actually a nice way around that. As I said, the log contains each value that was written. You know the mechanism, the formula that is used to calculate the values inside the TPM. And as long as you know the starting value in the TPM, which is actually defined by the specification, you can perform the same series of hashes, and you should get the same answer. So you go to the TPM, and you ask the TPM, what is the hash in register 5? And then you look at the log, and you look at every write to register 5, and you perform the same series of hashes, and you see if you get the same answer. And if you do, then the log file is trusted. You can now look at every entry in that log file, and you can make a decision about whether that specific log entry was a good thing or a bad thing. This has usually in the past been used for just as measuring binaries. You take a binary off disk, you measure that, and then you look at whether that specific hash value matches the hash value that you expected. We've gone further than that again, in that measuring the configuration file, when we're looking at every command that is running grub, there are cases where there are multiple equivalent commands that look slightly different but don't have any impact. So we actually store the specific string that was written into, that was hashed into the TPM. And that means that we can match against regular expressions. So you can write a rule that says, as long as this command matches this regular expression, it's trusted. So we replay the logs, we make sure that you get the same PCR values, but how do we know that the value we read from the TPM really came from the TPM? If someone's compromised the operating system, they could just modify the operating system to give us back the values we expected. And this is where we get into something called quoting. The PCR has an embedded key called the endorsement key. The endorsement key is associated with a certificate that gives you a chain of trust back to the TPM manufacturer, so you know that you are speaking to a real TPM. The TPM can then generate what's called an attestation identity key, which is signed with the endorsement key. So the combination of this chain of trust back to the TPM manufacturer for the endorsement key and this attestation identity key that is signed with the endorsement key means that you know that the attestation identity key came from that TPM. The TPM gives you the PCR values, the measured values, and it gives you a signature from that attestation identity key. And that means you know that these values really came from the TPM. If the operating system interfered, then either it would be signed with a key that doesn't correspond to the TPM, or it would be an invalid signature. And in order to avoid replay attacks, there's a random value that is given to the TPM by whoever's asking for this attestation, and then the TPM signs that as part of the blob. So you read that back, you verify that the information you got back included the random value that you gave the TPM, and that makes it impossible for someone to stash one of these and then replay it later. So we now have a mechanism by which we can obtain strong guarantees about the contents of the registers. We can look at the log file, we can verify that the log file contains accurate values, and what more do we need? Problem is, how do we know that the values, the log entries, are valid? How do we know what acceptable values are? What mechanism do we have for taking these 20-byte hashes and saying, yes, this is a good hash, versus no, this is not a good hash? For the operating system components, this is not too difficult. CoreOS, alongside every release of the operating system, ships a zip file that is signed with the same key as the operating system, and which contains the known good values of every component of CoreOS. We are the first operating system to do this. Right now, if you want to find out the acceptable expected values for Windows, you can't get them from Microsoft. If you want to know these for Red Hat, again, you can't get them. If you want them for anything, you're going to have to calculate them yourself. So we're shipping these values. You can download this zip file. If you perform an upgrade, you get the new policy file with that, and then you can compare against the new policy. So, easy. You know the values are correct because we told you that they're correct. Unfortunately, that's not all we're measuring. We're also measuring things like the system firmware. We're measuring components that came from the hardware manufacturer. And we can't tell you those values. And unfortunately, right now, typically, the manufacturer will also not tell you those values. And with luck, in the future, this will change. If you get a firmware update, it should come with the expected PCR values, the expected TPM measurements that would go with that version of the firmware. But until we get there, unfortunately, the best we can do is give you a command that's part of CoreOS. You run that on one of your machines. It gives you the values for that machine. So you get a new machine, you take it out of the box, you do this, and then those are the values that you would expect for any other systems that are identical to this system. Suboptimal, but unfortunately the best we can do right now. But we're here because we care about containers, and so how do we build this into the container ecosystem? And the answer is that we put this validation code in Kubernetes, because Kubernetes is the thing managing your containers, it's the thing scheduling them. If a machine isn't trusted, the desired outcome is firstly that you get told that the machine's not trusted, and the second desired outcome is you don't run any containers on it because it's not trusted. Something that runs containers on there and then sends you an email saying, oh, hey, this thing that we just deployed a container containing a bunch of secrets to says it's not trustworthy. Maybe you should check on that. Yeah, not particularly helpful. So we've been implementing this in Kubernetes in order to ensure that you don't do this, that you don't give secrets to nodes that do not have trusted values, that you do not run containers on those that do not have trusted values. So, hooray, doing it in Kubernetes. Obviously the right answer. Unfortunately, this isn't upstream yet. We're still involved in active development. We've been collaborating with the upstream Kubernetes community in order to find a solution that's acceptable for upstreaming. And so far, we're still maintaining this code as independent patches. However, we have found a straightforward implementation that appears to be accessible to upstream, and which is very, very simple, does not have any particularly invasive impact on Kubernetes itself. And the answer here is that Kubernetes has the concept of admission controllers, things that sit in front of the API and which say yes or no to certain requests. And one of the things they can do is modify what goes into the Kubernetes API. Kubernetes will shortly have support for something called taint, the idea that nodes can have some property, and by default, any tainted node will not have pods scheduled on it. Pods will have a concept of tolerance. If a pod is marked as tolerating that particular kind of taint, then the scheduler will run this. So by default, we'll have an admission controller that simply marks every node as untrusted, and therefore by default, pods will not run on that node. We then have a separate daemon that sits out of process and connects to the Kubernetes API and watches for node creation. And when it sees a new node being created, it then reaches out, communicates with the TPM on that node, and determines whether or not that node's booted in a trusted configuration. And if it did, that external daemon then clears the taint from the node. The nice thing about this is that the model is then not restricted to TPM-based trust. If nodes are by default untrusted, you can use any mechanism you want to verify the trust. And I'll go over a couple of things related to that later. So we're looking at this being pretty straightforward within the Kubernetes 1.3 timeframe. And obviously, we want all of this code to be upstream. We are very focused on it being available to everybody without them having to run out-of-tree patches. The policy that we apply exists within the Kubernetes API. There's basically policy objects that we create within the API, and so it's very easy to call out to Kubernetes and determine what policy exists. It's then possible to give authorized agents the power to inject new policy. So, for instance, you bring up a new type of node, or you do a firmware update, the expected values change. You want to be able to add those new values, and you don't want to have to tear down your cluster to do so. Simple. You just inject some new policy into the API. You can look at what policy exists. You can just delete this. We're doing all of this with third-party resources. And then, like policy, TPM data exists within the Kubernetes API. When a new TPM appears, we store that data in the API. And that allows you to pre-provision TPMs. That allows you to set a policy where, rather than saying, I will allow any new TPM that turns up to be part of the cluster, you can instead say, I will only allow TPMs that I have previously seen to be part of this cluster. And then you can add the TPM data in advance, inject that into the cluster, and then only systems that come up with that TPM will be trusted. And this is very powerful because it means that you no longer have to rely on YOLOing your secret distribution. So right now, you bring up a system in a data center. How do you know that the system that came up is your system? You order 200 new servers from a vendor, you get them shipped to the data center, they get wrecked. How do you know nobody tampered with them in the process? That's a difficult problem to solve. Right now, you can either have these systems shipped to you, and then you install the secrets on them, and then you ship them off. But when you do that, someone could again intercept them in transit and obtain your secrets or compromise the system. You can send them to the data center, and then you can send a person to the data center. Unfortunately, shipping a person typically costs more than shipping a server. And then that person has to spend their entire day repeatedly plugging a USB key into a bunch of servers in order to get the secrets on there. Or alternatively, you can just assume that the systems are safe and distribute your secrets, and it's probably fine. Yeah, I don't particularly like that idea. So instead, if you know the TPM key in advance, you can pre-provision all the TPM data. And that ideally would be done by the vendor shipping you the TPM data when emailing you the TPM data when you order the systems, when they ship. Alternatively, you can get the systems shipped to you, extract the TPM data from them, ship the systems off to the data center, have them racked, make sure that they match the values you read off them when they got to you, and then, again, you're fine. You know that the systems have not been tampered with in the intervening time. So that's really powerful when it comes to shipping systems, when it comes to deploying things to data centers that's not entirely under your control. Now, obviously, we want to tie this into the CoreOS product line. So all the components I've spoken about so far are going to be part of the upstream projects, or at least we hope that they'll be part of the upstream projects. We're also adding information. We're adding support for this to Tectonic. And so I'm going to show you some things which are how we're currently implementing this. This is not guaranteed to be the final state of things. But A workflow would look something like this. You bring up a node, and then you have some information in the Tectonic management console that tells you whether a node is trusted or not. And then if you drill down into this, if you click on a node that's not trusted, you'll get some more information about what event led to that machine not being trusted. So for instance, you might have an aspect of the grub configuration didn't match what we expected. And then we can provide you with what was given to grub, and you can look at that and you can figure out, oh, yeah, this has been tampered with in some way. I was not expecting the cloud config to come from that source. That's a machine that's out of my control. Someone's modified the configuration to pull down the configuration from a hostile system. And then, look here, you just have this, well, okay, overall I can see that everything else looks good, it's just this single component that was apparently not trusted. Like I said, the final shipped implementation may not look exactly like this, but this is the level of functionality that we are implementing. But we can take this further. We're not just measuring the boot process. Rocket has support for measuring containers into the TPM when you start a container. You bring the container up, the container image is hashed, and the configuration that's part of the container is hashed, and that's pushed into the TPM. And that means that when you ask the TPM for the log, when you ask the TPM for the PCRs, you also have a cryptographically verifiable log of every container that was brought up on that system, plus the configuration that was part of that container. If someone later compromises the system, the worst they can do is delete the log or modify the log, but you'll then know that that log's been tampered with, because when you replay it, it won't match the PCR values in the TPM. So this gives you absolute knowledge that your system was secure up until a certain point. Obviously, if the system's compromised, you can't trust any future log entries, but you will know that the system was fine up until that point and then changed afterwards. And longer term, what I've been talking about now is only possible on systems that have actual physical TPMs. There's a specification for virtual TPMs or VTPMs, which allows for TPM use in the cloud. Currently, no significant hosting provider supports VTPMs, and we're not expecting them to in the particularly near future. But the hypervisor itself is effectively a trusted agent. If you have a mechanism where you can push information about what you're booting into the hypervisor, if you can then access that via the provider's API, you can get the same kind of trust without having to use a TPM. And we are working on implementing functionality for this for various cloud providers. Right now, we're still very much in the exploratory side of things, and it's going to be a while until we have results. But the design is such that it's going to be straightforward for us to simply use a different trust agent to make those calls rather than the TPM one. Kubernetes itself will not need any modification. Tectonic will work in the same way. And with that, I'm going to say thank you, point out, as I'm sure you've heard already, that we are hiring, and then open it up to questions for a few minutes. Yeah.
What about trusting BMCs?
What about trusting BMCs? BMCs are the baseband or baseboard management systems that are effectively independent computers that sit on your system and have a fair degree of ability to tamper with the rest of the system. And the answer is, yeah, there's not a particularly straightforward answer. In principle, a well-designed system will not permit the BMC to interfere with the running system in any way other than to reboot it or to update the firmware. If it updates the firmware, then the measurements will change. And so that should be visible. However, a poorly designed system may allow the BMC to access system components at runtime and, say, modify the contents of memory. The best answer there is don't buy systems that have poorly designed BMCs. There is active research in this field to determine how many systems are suffering in such a way. The other side of this is your BMC should never be accessible from the internet. They should always be on an entirely segregated network. There should be no means by which anyone can gain access to them in order to then compromise another system. The industry needs to go further here. We're going to need to see more work that allows us to verify that the BMC has not been tampered with. Right now, that's kind of a hole. And it's a great question. Don't have an amazing answer, but it's probably not a huge risk right now. Yep.
Yeah, well, if anybody's working on a new BMC, let them know.
So observation from the audience that there is interest in people working on new BMCs, and that's your...
I have a question, actually.
Yeah.
So, is there support in Ignition right now for dealing with the TPM? For example, in a pre-installation environment, actually checking the values in the PCRS. You actually know that before you install them.
So the question was, is there support in Ignition for verifying the TPM state before doing the rest of the things? That's a little difficult because if you're running on the system, you have no mechanism to communicate with the TPM without knowing whether or not your communications have been tampered with. The kernel could lie to you and give you back the values you're expecting. So local attestation is very, very difficult. You really need if you're doing TPM-based validation, you really need a remote system to do that. So it's difficult to do this at the Ignition level. You basically have to do the OS install and then have the OS verify to a remote system. And then the remote system decides whether or not to give you access. But you could potentially have a kind of gate point earlier in the boot process where the system does not get, if say you had an encrypted disk, the decryption key could be kept on a remote site, a remote system, and that key is only handed over if the TPM is in a known good state. And then the system can't boot any further, and then the system's not able to get onto your network and do damage. So there are some theoretical things that we could do here. Right now, we're not really looking at that kind of scope.
Well, the point of my question was specifically, given our scenario, we're actually providing the hardware. We know the BIOS, we know the firmware, and we reset that regularly. Could we provide that in known state to end users via this method?
Yeah. So I think the easiest way of handling a situation where you want to verify that the system is in a known state before handing it over to a user is to reboot into a small environment that does nothing other than perform an attestation. And then you can say, okay, everything is as I expected, everything is as I expected, and so I can return this to the pool and have someone else take over the system. Any other questions? Yeah.
Can you also verify the user configurations, like making a snapshot of the system? These are the keys that needs to be added, and there should be no other key to be trusted for other containers.
The question is, could you also validate and measure and validate userland configuration? Right now, we're not doing that. So it would certainly be possible for us to push any keys into the TPM. There's actually support in the kernel for measuring every executable that is run on the system. And we are considering whether that's going to be useful for various use cases. But certainly, right now, the implementation has been very much focused on our particular use case. As customers come up with further use cases, I think we're going to continue developing new functionality around this. We may end up measuring more things, and then we want to have this be as flexible and as powerful as possible. So that's actually a great suggestion, and I will look into what would be involved in doing that. We've got time for maybe one more question. Yeah.
So how does my app running within a container actually benefit from all that?
How does your app running within a container benefit from this? The app itself benefits because it's not then tampered with. The app is not subverted. The app is able to rely on the operating system running the app you thought you were running. It's able to rely on the operating system giving it the results it was expecting and truthful answers to questions it asks the operating system, rather than potentially malicious answers. And the aim is to avoid scenarios where you run a security critical app on your system and it is being given unreliable information by that operating system.
But what about the other way around? For example, making sure that only approved apps will be installed.
So how can you use this to make sure that only approved apps can be installed? Well, part of this is that Rocket already verifies the signature on containers. So at that level, you should already be skipping the you should already be refusing to run stuff. But like I said, if the operating system had been tampered with, that could also be tampered with, and then you might end up running unapproved applications. So yeah, this measurement means that you have confidence that when Rocket is running, it is performing the correct signature validations, and so you know that you are only running authorized applications. Anyway, I think we are right on time, so it's lunchtime now. Feel free to grab me if you would like to ask any further questions, but thank you again.